let x be a random variable that tracks the number of successes. Then x is a binomial random variable. Let p prime, put that little mark up there, lowercase p, once again we're abusing this notation, and n is the number of trials. Well, it turns out that these things, these proportions, that's what this is. So this is I guess you'd call them the proportions, or proportion of successes. These proportions do form a normal distribution. When, of course, n is large enough. So here's what we're going to have. This will be the sample proportion. And our confidence intervals will look like this. Here, the error is going to be the z-value times sigma over the square root of n. This turns out to be z times the square root of p prime times 1 minus p prime all over n. Now, in practice, this will be somewhat complicated for your calculator to do, so let me show you a couple things. I'm going to rewrite this in the following format. Z times, this is probably the way you'll want to enter it into your calculator. Now, your calculator may or may not allow you to allow the containment bar to grow as you type it in. So it's possible that you may need to do something like the following. And you may have to end the parenthesis so it knows what all is inside of there. So if this is for those who will only do a small one. Of course, Desmos has no problem with fractions at all. For the purposes of using a table, the z-value will be p prime minus p divided by the square root of p prime times 1 minus p prime slash n. And you can do that all on one line inside of that square root there then. This will be our z-value when we're using the tables. This here will be the z-value when we're computing things like the error and a size of the population needed to achieve the error that we're looking for. All right, here we have this guy right here is going to be our n. This 98 here is going to be our x because we're considering that to be x. If you own a tablet, is considered success since we are doing the study on people who own tablets. The confidence interval is 95%. So you might remember when you look at this, there's a graph associated with it. And then there's a z-value here, and we have 95% in between, and then we have another z-value here, the negative z-value. So what that left out in each space was 2.5%. What I really wanted, since if we're looking at the error, take a look at the error. The z that we're going to find is the z that we're going to use in this formula. So we go and look up 0.975 in the table, and we've done that before. I'll do it again just to remind you. This is 2.5% is a sort of specialized. What I'm going to do is try to look up the z-value that's associated. Well, I don't know. I guess you could look up a z-value that's associated with 2.5%. But I'm going to look up mine associated with 97.5%. So let me go ahead and pull that up. All right, I brought up the relevant portion of the table. I see 0.975 right here. That's 1.96, and it's one of the only ones that works out so beautifully. So for this, we are going to have z is going to be 1.96. Now, as far as the p prime in that, let me get the square root started, not a parenthesis. For the p prime, it's probably not a bad idea to calculate it and get the decimal. So let me do that. This equals 0.392. So let's go ahead and put those numbers in. I have 0.392. So I'll put this one in here too. This is 0.608. And then divided by 250. Probably it's not going to be so bad. I'm going to do the square root on my calculator. Your calculator undoubtedly has a lot more capabilities than mine does. So very slightly over 6% is our area. Now this here, this p prime, is what we're going to center our interval at. So this is going to, remember, it's p prime minus e, comma, p prime plus e. Our p prime was 0.392. So somewhere between 33, roughly 33 and 45% is what our true proportion is. That is to a 95% confidence. This next example is actually two different examples at once. Part A is actually completely different than Part B. So I'll just concentrate on that part for now. So here we have a survey of 600 students. There is our N. 480 voted against something. So we'll use those votes as being against, as being successes, because we are looking at the students who are against the new legislation. And there's our confidence interval, 90%. So while I'm here, let me go ahead and get my P prime. That's 480 divided by 600. That's 0.8. 1 minus P prime will equal 0.2. And a 90% confidence interval will look like this. So we want 90% in here. Out here we want 5%. And over here we also want 5%. This is one we've done before, but really what I'm interested in is the z value here. I want the positive z value. And you can find that by going into the table and trying to find 0.95. Let's see what happens. All right, here's the relevant section of the table, and I see that 0.95 is trapped between two values, 1.64 and 1.65. So I will take the average, 1.645. So here, once again, z times the square root of p prime times 1 minus p prime slash n. Now let me see, what was our p prime is 0.8. So we have 1.645 times 0.8 times 0.2 divided by, what was our n again? Our n was 600? And then our confidence interval. That equals p prime minus e, p prime plus e, so we can contain the true proportion is somewhere roughly between about 77% and a little under 83%. Once again, another calculation we will be interested in is the size of the sample that you need to achieve a certain kind of an error. So for example, we know this. Error equals z times the square root of p prime times 1 minus p prime. Now I'm going to write it slightly differently than before. Like that. And then what I'm going to do is the following. I'm going to write z over 1 and e over 1. You'll see why in a minute. I'm going to leave e over 1 as it is for a little while. The other side, I'm going to write z times p prime times 1 minus p prime. And then all of that will be over the square root of n. I made a mistake in this right there. So we'll cross multiply. If you're not following this, it's not a big deal because I'm going to show you the formula when all is said and done anyways. So what we're going to have is e times the square root of n equals 1 times z times that square root. Now I'm going to divide both sides by e. In the next step, I'm going to square both sides. You may recall from previous times that when you square something like this, you square each and every piece inside of there. So for example, I'll square the z, I'll square the square root, and I'll also square the error in the denominator. So this is my formula for n. It's another one that you're going to want to keep with you. The next example will illustrate it exactly. Now there was a part B to the problem that was seemingly unrelated to the problem itself. Here we have a sample of 300 students, 68%, so P prime, it's easier to work with decimals than any other kind of numbers, so I'll write 0.68, and we want a 97% confidence interval. So when we draw this out, this helps you get your z value. What I want is 97% between these two z values, which means that what's left in here is 3%. So if you take 3% and divide it by 2, we get 1.5% in each n. So what you can do, 1.5% is 0.015. You could choose to look up 0.985 in the table, which is what I'm going to do. So I'm going to look up an area of 100% minus the 1.5% in the table. And that equals 98.5% in the table. Here's the relevant portion of the table. Let me see if I can find 0.9. Oh, look at this. 0.985 is right there. It looks like we are at 2.17. So z equals 2.17. Now let's grab my formula. Well, so my error maybe let me write out the basic formula first. And now we're ready to put 2.17 in. P prime, let's go back up and see what that was. 0.68. Which means that 1 minus P prime would have been 0.32. And then N was 300 in this sample. So that's almost 6% error. And then our confidence interval, that will equal, if you want to convert to percentages now, that's perfectly fine. Percentages are wonderful for giving people an easy way to read information. So you certainly could do it this way. So a little more than 62% and a little less than 74%. Now, I was a bit premature in my calculation earlier. I forgot that there was a part B to that problem. So let me go ahead and put down how we get the size of n again. That'll be our formula for n. All right, a marketing company is doing some research. They want a 90% confident interval. And they say, how many customers should the company survey in order to be 90% confident that the estimated proportion is within 5 percentage points of the true proportion? So right there, this 5 percentage points here, that's the error. And instead of percentages, you're better off putting it in that format. Now the 90% confidence interval is related to the picture and the z-value in this way. That means we leave 5% in each of the ends. So what I typically do is I look for this z-value, so I'm looking for a 95% in the area of the table. We've done this one a few times now. It's 1.645. And now let's make use of the formula. So z squared, that was equal to 1.645 squared. P prime we don't know it. Where's P prime? Well, we don't have it. So this is what they do when they don't have it. If P prime is not given, we assume that P prime equals 0.5. The reason they do that is it makes the P prime, which is what, 0.5, equal to the 1 minus P prime, so they're both 0.5. But the product of the two of them is as big as it can be. So any other two numbers that are between 0 and 1 that I matched up and multiplied, they would be less than 0.25. So the whole point of this is maximizing that number, and that's what you do when you don't know what the sample proportion is. But usually you do know what the sample proportion is, but you don't have to. You can do this little trick to get yourself out of that difficulty. The error was 0.05, so we're going to have 0.05 squared. So we're going to have to go ahead and calculate this whole thing. Now this calculation you do not have to take very much effort in, because we're just looking for a whole number for our answer. This is a situation where we know that 270 is not quite enough, so we need to round up to 271. And that is the end that you'll need to accomplish an error of plus or minus 5 percentage points. Here's an example from the practice section of the current textbook we're using. And number 62 follows these instructions. So we're designing a study to determine the population proportion. So what is this? They're interested in knowing the population percent of women who make the majority of household purchasing decisions. So when designing a study to determine this population proportion, what is the minimal number you would need to survey to be 90% confident that the population proportion is estimated to be within 0.05? So once again, this right here, 0.05 is our error. 90%, we just did one in the last problem that did that. Z is going to equal 1.645. And then they don't, nowhere is P prime given, so we're going to assume that P prime equals 0.5 since it's not listed. That means that 1 minus P prime is also equal to 0.5. So my N will be 1.645 squared times 0.5 times 0.5 divided by 0.05 squared. And you'll see these are the exact same numbers from the previous problem. We're going to get 270.6. So we'll round up to n equals 271. Let's change a few things. What if we want a 95% confidence interval? So in this situation then, we have it like this. We're going to have 95% in here, leaving 2.5% out there and 2.5% there. So what I would look up in the table is try to find 0.975, and we have done that. In fact, this was one, it's very good, 1.96. And then our n then is going to be z squared times p prime times 1 minus p prime divided by the error squared. So we have 1.96 squared times 0.5 times 0.5 divided by 0.05 squared. My calculator gives me 384.15. I really don't care about that. We're going to round up to 386. Notice the sizes increase, obviously. To get more accuracy, you have to increase the number of people that you survey. What if we want a 99% confidence interval? Well, this is a bit different, isn't it, now? So this may require a huge, let's see how big it will require. So here's 0. So these are going to be really small here, z. And then the same over here somewhere, negative z. This time we're going to have 99% in here. That means that we're only going to have 0.5% out there. Well, that's equal to 0.005. So if you're looking for the area that ends at that z value and goes all the way to negative infinity, we're going to have to look up in the table 0.995 will be the total amount of area used up to that point. Well, let's see what the table tells us. Here's the relevant section of table. I'm looking for 9950 if I can find it. It doesn't look like I have it exactly. Here's 99492, 99506. So it's between 0.07 and 0.08, so I'll do 0.075, and that's attached to 2.5. So z will equal 2.575. So the corresponding n that we need here is 2.575 squared. And we still aren't told the p prime, so we're going to keep using 0.5 divided by 0.05 squared. Here we get 663.1, so round up to n equals 664. Here's from the homework section of the book that we're currently using. We have a survey of 400 drivers found that 320 claimed they always buckled up. So they have some information here. X is 320. We're going to use X as the number of people who do buckle up. N is 400. P prime let's see, I believe that's 0.8. It's going to be easiest if you put in to a decimal form. Define the random variable x. X is the number of successes. We could look at it this way. X, whenever you're doing any kind of a survey, X could be the number of people that are associated with those who buckle up. P prime, these are the proportions of bucklers. Probably I should say the proportion of the population who buckle up. Which distribution should you use for this problem? Well, P prime is approximately normally distributed. And as n gets larger, it will become even more normally distributed. For D, we want to construct a 95% confidence interval for the population proportion who claim they always buckle up. So we need the confidence interval and everything like that. Well, let's first get the 95% Z-score, which we've done it a lot of times by now. Here, 0, and remember we want a Z and a negative Z, and we want to trap 95% in here, which means that there's 2.5% here and 2.5% here. If you look up 0.975, this is a very good number for us. Comes out to be 1.96. And then we're ready for our confidence interval. So let's go and get our E. We can actually, there's another formula that we can use. Like so, and we'll put our P primes. This, as I remember, is the easiest way to do this. So our P prime was what? P prime was 0.8. That means that 1 minus P prime is 0.2. And the N, how many people were used here? 400. Here we get 0.0392. And then our confidence interval, I guess that's part I. Let's go ahead and do that. Confidence interval will equal P prime minus E, P prime plus E. P prime was 0.8. We just found our E, 0.0392. 0.8 plus 0.0392. This equals so it looks like it's trapped up between roughly 76 and 84%. What else did they ask us here? Sketch the graph, okay? I think that's what they're talking about here. So RP is, and maybe they're talking about just the interval itself, I don't know. But let's draw a picture of this. RP prime was 0.8. So we'd have 0.8, and then we would come up to 0.8392, and then back here to 0.7608. The error we were trying to accomplish was 0.039. Well, that is the error we did accomplish. So those distances there are 0.0392. We were 95% confident. So we have 2.5% here and 2.5% over there. Calculate the error bound. Well, there it is right there. Error bound means E. So there is your error for the problem. Here is an odd example, but it's one that's very useful to at least the military. It seems that when soldiers are put out in combat situations, a certain percentage of them purposefully do not shoot at human targets. They will miss on purpose because well, for a variety of reasons. Maybe they just don't want to kill people is probably the most obvious reason. I'm sure there's other reasons, but that's not the point of this here. Let's just get ourselves a 95% confidence interval for the true proportion of soldiers who purposefully miss their targets. So what we have here is an N of 1,000. Here's our X. And then our P prime is X over N. So we have 152 over 1,000. Which is 0.152. Then 1 minus P prime would equal 0.848. And if we're doing 95% confidence interval, we are going to center it. Well, actually, when I'm talking about 95%, remember, we go and look up the z-values from the standard table, so it looks like this. And then 2.5% here, and 2.5% there. So we've done this a million times. This is 1.96. So let's go get our error number. E equals so our z here is 1.96. Square root p prime is 0.152 times 0.848 slash 1,000. 1,000 is a pretty good size sample. So the error is a little over 2%. And then we're going to look at our confidence interval. As you recall, that is p prime minus e times p prime plus e. So we have 0.152 minus 0.0223, 0.152 plus 0.0223. So based on this estimate, the number of people that actually purposefully try to miss their targets is a little less than 13% to a little less than 17.5%. You should know that the military is fully aware of statistics like this, and they adjust their strategies and attack positions and everything else with these statistics in mind.